All right, kiddos. So apparently you're having trouble getting onto Pearson. So I'm going to go ahead and just play it from my computer and do a screen recording. So my apologies if you happen to hear Max. He's doing his e-learning as well. And yeah, so I'm just going to play it from here. And then you can still do your questions and everything like normal on Canvas.
Wave interactions. Guiding questions. How do waves interact with different materials? How do waves interact with each other? Connection. Literacy. Integrate information. Vocabulary. Reflection. Refraction. Diffraction. Absorption. Interference. Standing wave. Resonance. Academic vocabulary. Transmitted. Hands-on lab. You investigate. See what type of interference you get when you send waves down a coil. Look at the goldfish shown swimming in a glass tank. Place an X on any fish that you think is a reflection. Download to complete the activity. Connect it. Use evidence. How many real fish do you think there are? Construct explanations. Why is it difficult to count the number of fish in the tank? Reflection, refraction, and absorption. If you've ever been to the beach, you've seen how different kinds of waves move. Some ocean waves crash into rocks or piers, while others reach the shore smoothly. Rays of sunlight hit the surface of the water, and some bounce off while others pass through. In general, when waves encounter different media, they are either reflected, transmitted, or absorbed. Reflection. Some waves are completely blocked by an obstruction, but their energy is not absorbed or converted to another form of energy. These types of waves bounce off or reflect from those obstructions. In reflection, the wave bounces off and heads in a different direction. The law of reflection states that the angle of incidence equals the angle of reflection. This means that the angle at which the wave strikes the material will match the angle at which the reflected wave bounces off that material, as shown in Figure 2. Light reflecting from a mirror is the most familiar example of reflection. The echo of a voice from the walls of a canyon is another example.
Refraction. Imagine riding a bike down a smooth asphalt road. When you turn off the road onto a dirt path, the transition can be jarring. You might have to grip the handlebars hard to keep the bike going straight, as the two wheels are on different surfaces. When light waves are transmitted from one medium into another, they also bend in different directions. This bending is due to refraction, or the bending of waves due to a change in speed. When a wave enters a new medium at an angle other than perpendicular, it changes direction. For instance, when light is directed at water at an angle, as in Figure 3, the light slows down and bends downward. The wavefront bends toward the normal, the imaginary line that runs perpendicular to the boundary between the two media. Academic vocabulary. What is another way for saying that a wave is transmitted through a medium? Planet. SEP. Develop models. Have you ever seen a movie scene in which a character appears to be looking at a mirror, yet the camera is not visible in the mirror? Think about how the director set up this scene. Draw a setup that shows the position of the actor, the camera, and the mirror, and demonstrate why the camera's image is not visible to the camera. Download to complete the activity.
Refraction, figure 3. Light rays bend as they enter water because one side of the wave front slows down in water while the other side continues at the same speed in air. So here you have beam of light, air, wave fronts, and water.
Literacy connection. Integrate information. As you read, classify the phenomena you learn about as either interactions between waves and media or interactions among waves. Diffraction. Did you ever wonder how you can hear someone speaking even if they are around the corner of a building or doorway? This is an example of diffraction. Waves don't only travel in straight lines. They also bend around objects. You can observe diffraction with water waves as well as sound waves. Water waves can diffract around a rock or an island in the ocean. Because tsunami waves can diffract all the way around an island, people on the shores of the entire island are at risk. Absorption. When you think of something being absorbed, you might think of how a paper towel soaks up water. Waves can be absorbed by certain materials too. In absorption, the energy of a wave is transferred to the material it encounters. When ocean waves reach a shoreline, most of their energy is absorbed by the shore. When light waves encounter the surface of a different medium or material, the light waves may be reflected, refracted, or absorbed. What happens to the waves depends on the type of material they hit. Light is mostly absorbed by dark materials, such as the surface of a parking lot, and mostly reflected by light materials, such as snow. Reflect. What are some ways in which you can use reflection in your everyday life? Are there things you have to keep in mind when you use reflective devices, such as mirrors? Question it. Classify. Identify each picture as being an example of reflection, refraction, or absorption.
Question it. Classify, identify each picture as being an example of reflection, refraction, or absorption. Wave interference. Have you ever seen two ocean waves collide from opposite directions? So they momentarily form a bigger, hill like shape before continuing in their original directions? This is an example of wave interference. There are two types. Constructive interference. The example of two waves of similar sizes colliding and forming a wave with an amplitude greater than either of the original waves is called constructive interference. You can think of it as waves helping each other or adding their energies together. As shown in figure 4, when the crests of the two waves overlap, they make a higher crest. If two troughs overlap, they make a deeper trough. In both cases, the amplitude of the combined crests or troughs increases. Types of interference, figure 4. Write captions to describe 3 parts of destructive interference. Complete the key to explain what the different arrows mean in the images. Destructive interference. When two waves combine to form a wave with a smaller amplitude than either original wave had, this is called destructive interference. Destructive interference occurs when the crest of one wave overlaps the trough of another wave. If the crest has a larger amplitude than the trough of another wave, or of the other wave, the crest wins and part of it remains. If the original trough has a larger amplitude than the crest of the other wave, the result is a trough. If a crest and trough have equal amplitudes, they cancel each other out. as shown in Figure 4. Destructive interference is used in noise-canceling headphones to block out distracting noises in a listener's surroundings. Reading check. Infer. Which type of wave interference could cause sound to become louder? Explain your answer. Interfering waves. Figure 5. Ripples created by rainwater on a pond interfere with one another in a pattern that exhibits both constructive and deconstructive interference. Hands-on lab. See what type of interference you get when you send waves down a coil.
Standing waves. Look at the rope setup in Figure 6. The rope is tied to a doorknob, and someone shakes the free end. This motion can generate standing waves. A standing wave is a wave that appears to stand in one place. Standing waves are produced by two waves interfering with each other as they travel in opposite directions. Standing waves on the rope appear when an incoming wave and wave reflected from the doorknob have just the right frequency to interfere as shown. In a standing wave, destructive interference between the two colliding waves produces points with zero amplitude, called nodes. The nodes are always evenly spaced along the wave. Points of maximum amplitude on a standing wave are called antinodes. Antinodes always occur halfway between two nodes. The frequency and wavelength of the interfering waves determine how many nodes and antinodes the standing wave will have. When seen in real life, the antinodes appear to pulse in and out from the rope's rest position, while the nodes appear motionless. Standing waves can sometimes appear on lakes when the wind and pressure around them are just right. The water appears to have a node in the center of the lake, and the water wave rolls around that node.
Standing waves, Figure 6. As the hand shown at the left increases the frequency, the number of wavelengths present in the standing wave will increase. In a standing wave, it looks like there's a mirror image of both the crest and trough. Label the rest of the nodes and antinodes.
Resonance. Think about the last time you swung on a swing at a playground. You may have noticed that it is difficult to get yourself going. Once you are in motion, you can pull on the chains of the swing and pump your legs at the right time to keep yourself swinging. The swing has a natural frequency, and your actions match that frequency to create greater amplitudes in your motion. Most objects have at least one natural frequency of vibration. Standing waves occur in an object when it vibrates at one of these natural frequencies. If a nearby object vibrates at the same frequency, it can cause resonance. Resonance is an increase in the amplitude of a vibration that occurs when external vibrations match an object's natural frequency. When soldiers march across a bridge, they make sure to stay out of step. If they did not, their footsteps could cause the bridge to swing wildly like the rope in Figure 6 and collapse. Understanding resonance of different materials is also useful for people who build guitars, violins, or other wooden string instruments. If the wood in a guitar, such as the one in Figure 7, resonates too much with a certain note, it may sound too loud when that particular note is struck. Likewise, if the wood does not resonate with any particular note, the instrument may sound dull. Reading check. Summarize. In general, why is it risky to build something with a natural frequency that can be matched by external vibrations? Make meaning. Make a 2-column table in your notebook. Use it to record descriptions of constructive interference, destructive interference, standing waves, and resonance.
All right, sixth graders. So now your task is to go into Canvas and access your questions, reflect on those questions, answer them to the best of your ability, and get those posted in our Science Canvas course. Thank you so much for your patience and your communication with me, letting me know that you were having an issue with Pearson Realize, and we apologize for that. Thank you. Stay safe, stay healthy, and wash those hands.